Hi, I'm Kapil. When it comes to ML compute accelerators, what are the features that it would have that would make it a winning product? Let's dive in a little bit on that. This video is not an architectural insight, but more of wearing the product management hat. Now, these requirements can serve as a start point of architecture exploration or review, or some comparison perspectives, or some aspects of the product strategy. I think this video can be useful as a one-on-one insights for all executives and investors in the field of AI infra. So the requirements. One is the low latency execution. Let's say for the inference, you would like how much time it takes to generate the first token, how much time the first full output can be generated. In case of an image generation, how much time does it take to generate the image? Similarly, for the training, for the given number of accelerators and the given data, the kind of model that you want to produce, how much of the training time it will have, that is one requirement that decides the better it is and the better the product is. Then other aspect is the low cost. Both the recurring expense and the non-recurring expense are amazingly high. And that's why they come in the forefront for the requirement side. For inference, you can view it in this way. The cost per inference, where you amortize the non-recurring expense value as well into it, is what decides. If you can do it cheaper, it's good. Similarly, for the training, how much it costs to do the pre-training or to do the fine-tuning later. I have not put the fancy data into these foils, just to keep the foil simple and my effort lower. But just for the perspective, one pre-training itself costs to the south of $100 million plus nowadays for the training. Just to give you the perspective that it's a huge money that is going up into it. We all know that. Now, we talk of the very high level of this, and we are done with these two requirements, just do it fine. But that's too high level. Let's go a little bit deeper. So for that, uh, let's dive in on that. So one thing we have to understand is this whole ML compute acceleration is actually a very close tied co-design effort. Most big time, the whole whatever is happening in the put in hardware and whatever is in the put in the software is to be really in sync in a close way. In fact, 75%, I would say, uh, of the beauty of what we get in acceleration is actually on this software side of the circle of it. Now, hardware will say, I'm just an enabler. I ensure you the things that you pass to me, I'll be taking them in a very streamlined way. And software will say that, hey, I understand your constraints, your electrical constraints, your thermal constraints, and the semiconductor physics aspects of it. And what I'll do is I'll work my best to mitigate those at my level, to land in the optimization around various inflection points. With that, let's dive in further in the requirements. So latency and throughput, we talked that less first token time, generation time of the first token is one of the requirement lists just for the example. What do we really do out for that thing? So one simple thing is MLs are all about huge number of compute. So one obvious thing is you put high number of MAC multiply accumulate blocks and you increase the count of them and you do them with the efficient data types that's barely needed for that ML applications and don't overdo on that. That is what achieves us the maximizing the compute thing. Now, another aspect is the memory bandwidth, where it includes the accumulators in the hardware or the on-chip buffers and the on-chip memories and the off-chip memories combined. The throughput that they offer and utilizability of it is what avoids the bottlenecks. But is that it? No. For the edge devices case, there are two things, context switching and concurrent applications. They form an important requirement. For example, you take a phone, at a given time, there can be 4 or 5 applications that would be needing to do some kind of an ML compute. Either it will lead to context switching or same hardware concurrently being shared across the 5 applications. So this becomes ability to do that becomes a good value add as a requirement for the AI accelerator working at the endpoint. So it applies to the phone, the laptops, or the cars for that matter, or the robots that will come up in the future. Another aspect is the batch processing. Batch processing is, as we saw, software was saying, hey, I understand your constraint and I'll do things to help you. Batch processing, one such optimization. There are hardware limitations. It turns out that one way that could be did and we can increase the overall throughput is through the batch processing. But what hardware needs to do is, is it optimized? Is it designed in such a way that it really makes use of the batch processing in a good way? So that is one requirement that comes by. Then another requirement is the scale out performance. This is a full topic in itself. Let me just explain it out a bit. So what happens is if you have one ML accelerator and the model that you're running is huge, so can you have that model somehow the overall compute that partitioned across the ML accelerators? Let's just say, for example, 5,000 ML accelerators. So you are dividing the whole compute across the 5,000 ML accelerators. And that aspect is called the scale out. So when you keep on adding more and more, how the performance scales, is a very important capability of that accelerator and the system around it. Let's dive a little bit more on the scale out side. So normally, if what compute you are doing here on one accelerator and on the, if they're totally unrelated, then you would expect that as on the x-axis side here is shown the number of ML accelerators, imagine, and on the y-axis you are seeing the speed up, overall throughput speed up that you're getting. You'd expect it to be linear if it's uncorrelated. However, when you divide one problem compute into several parts, the inherent subscaling overheads come by, and what it would mean is that those factors will tend the utilization to be less than linear, which is in the sublinear space that is shown in here. There are several factors of it that come by. However, there is also some factors which are superlinear, which means moment you split a model compute on more than one resources and add more resources, let's say from 100 ML accelerators, you move to 200 accelerators. You not only just move the compute capacity to twice, it actually goes more than twice. And that aspect is called the superlinear thing. So what happens in case of an ML accelerator aspect is that initially the superlinear will dominate. That means if you keep on adding the more ML accelerator and split the compute across them, you get more than linear benefit. Slowly, a point comes where it becomes a linear, because at that time, the sublinear effects are starting to dominate and the superlinear start to fade in. And beyond that count, let's just say for the sake of discussion, 5,000 ML accelerators. Beyond that, if you'll keep on adding them, you will have a diminishing returns further. So that's just to understand. So from a system level perspective, you'll see that there'll be a number that will have more compute offering than the lesser of it. So this is a very good sweet spot of this one. Okay? Let's just understand the business aspect of it. So let's say you have some business has a requirement that, hey, I want to do the training and I want to finish it off in a 6-week time frame. One option of hardware and software whole stack is, which says that if you keep 10,000 accelerators, this training can complete in 8 weeks, let's say. But if you make it 20,000 accelerators, it can reduce the time from 8 weeks to 6 weeks. There can be another option which is able to reduce it to 6 weeks with not 20K needing 20K accelerators, but 16K accelerators. So now you can see that the second option is allowing 6-week training time while needing 4,000 less ML accelerators, which is straight away adding to the cost benefit of it. Thus, this is the way you can just appreciate the business requirement for the scale out performance. And a lot is being done on the architecture side towards solving out on that one. Let's get into the cost metric. This is what we glimpsed upon as well in the first foil, high level. Now we'll dive in a little bit deeper. So the recurring expenses are no less, and it is very significant. So one is the electricity consumption because of the power consumption in the chips and the electrical components. The cooling solution itself, lately, water cooling is also used up as an option to have a more effective cooling. And that cooling has its own, what do you say, inefficiencies. So you consume a lot of power in maintaining that cooling solution itself, etc. And we all know the non-recurring expense, the hardware itself cost of setting up a data structure, data server, and the cooling setup itself is no less. So these components itself, each of them runs in a few millions if you really made up a one data center of AI center. One of the metric that we can see is how many inferences per second per dollar the cloud is able to perform. And we can have the amortized value combining all of the expenses that you have made up for that thing. So you see that energy efficiency comes up as a key component uh, in this game, and because that decides the electricity that you consume by. An electricity bill runs up in a few million dollars, a few $100 million itself is a very significant thing in its sector. One of the units that has been really used up lately is TOPS per watt. It does reflect in the first order, but not really a key, the metric which is informing all the things. So joules per inference would be a better metric just for the sake of discussion right now. How many joules does it take to do the inference? Decides the full capability of the full stack, including the software as well as the hardware combined overall. Now, for the edge servers and the cloud, if you are able to make more energy efficient systems, you are directly affecting the cost per inference and thus the value add of the product feature. Even for the battery driven devices, actually, more than the cost of that way, it actually directly decides the USP. These devices, if they hog the power, uh, it's that's like that use case, that ML use case is not really supported on the device in that sense, truly. Now, one interesting thing is that these battery driven devices, some of them are actually operating in the milliwatt range, uh, and still they want the ML compute there. So you see broadly, what you can see is right away we can think that a different architecture, different designs will be needed for the product set which are operating in the milliwatt range, and some for the few watts range. Let's say the mobile phones and the laptops fall under that category. And then comes the edge servers and the cloud servers. So broadly, three categories for sure right away come up based on the energy efficiency segmentation itself. And they will have a different design choices, different architectures for that, and so on and so forth. One point that I want to highlight is this whole costing thing brings up very interesting inflection points around it. When the hardware cost is too high, the chips are very costly at this point of time, and the availability of chip itself is low. What alternate comes in is let's have a better cooling solution. Through better cooling solution, each chip is performing a little bit more than what it could, and thus you are able to meet the requirements for it. So this is how the system level requirements are being driven more by the chip shortage as well as the cost of the chips. When the cost of the chips go down in future, the considerations of reducing the cost on the cooling solutions will also become more dominant at the same time around that. And that's what changes the landscape about it. Now, can there be one hardware software architecture that fits the bill for all? Answer is no. And as we saw in the last point itself, we saw that even different energy efficiency segments will need the different architectures and the different design by large. Actually, within the same energy efficient segment itself, uh, there can be various different winners possible around it. So when we say generalization, specialization, let's first understand that. So specialization could be that you build a hardware and software stack on top, which is able to do the image generation, but it's not good for anything else. Or vis-a-vis just a large language model for the text generation, not the multimodal or kind of a things. Vis-a-vis, there can be a hardware, the stack, that is able to do all of them. So this is a big product strategy choice that any company makes while selling, or as a buyer, you make when you're setting up your data centers. How much specialized should I be, or how much generalist should I be around that thing? To tell you the background of it, 10 years back, the products that companies were making, there was in the roadmap, you will see one product roadmap for the training and one for the inference. This is even before LLM era. Then in middle, few years back until recently, the product, this thing kind of diluted. And the same hardware was being used for the training and the inference kind of thing. Now, so many companies are there which are making the dedicated hardware for the inference. It's clearly established that the training hardware and the inference hardware better be separate and better be specialized for its aspect. There's the ROI for that. It's big enough a bucket to make a separate this thing. Now, so inference versus training becomes separate is kind of established now. Now, within that too, uh, this is the norm basically. So there have been companies that came up which are specializing in the training, specializing in the inference side, and on more on the generalist side by large, let's say. But that wave is, from a startup point of view, is past few years back. Right now, where the opportunity still lies for the new companies still is the specialized hardware. And I think that uh, for the specialized hardware in the cloud and the edge server space, at least there are three, four, five big sub buckets, sub segments are there, which are worth reasonable revenue and where the specialized hardware has a very great potential to dominate. And similar goes for the battery powered devices. There are good set of things could be there where a very unique, different specialized hardware could be there, which will serve a very compelling business ROI to enable certain use cases on the battery powered device. Now, before we go further, let's take a glance into what really happens when you write an application till it is actually run on the hardware. So, application is developed, let's say in Python, using a framework, let's say TensorFlow. Now, what the flow, this is just a high level flow I am giving. It's not really every time this way, just a symbolic, uh, conceptual way. So, what really happens is it's compiled up and a graph, compute graph is generated as one step. And then this compute graph is split up, is partitioned up and optimized as a next step. Further, it is lowered to several internal representations in the compile steps further. And it gets mapped to the search, either that the divided graph is mapped to a certain kernel, which is an optimized handwritten code available, or non-kernel, but like the code is generated out for that. Then this kernel mapping, this kernel and the code gets actually compiled to the machine code. This is what actually runs on the hardware. So imagine on the right side of the orange arrow is the sitting the hardware. So one thing that we have to see is it is this total thing that has to be really streamlined to each other. That's where the ROI comes by, as we had seen earlier. So as I'm highlighting it for the third time right now, the real battleground of who wins, how the things is going to be, is around the hardware stock, software stack, seamlessness to each other. Let's dive in some specific aspects of this thing. So one is the execution model choice. Though it's an architectural choice, it's big enough to be called as a product requirement. So one paradigm is, let's say, for example, in this case, is SIMT, which is followed by NVIDIA GPU and several other, most of the GPU. And then there's another approach called data flow, which does not go by the program counter, doesn't keep the notion of thread, but rather the keep it as a data flow graph itself. And that approach is being followed by the companies like Sambanova and Grok of the world and Cerebras, etc., and several other companies. And this makes a huge difference of the choice about for them and this thing. One thing is that it's a gray. It's not like somebody is perfectly SIMT or things like that. So overall stack gets mixed up actually. Voilà. Another very key aspect is the dynamic workload handling. What I really mean is this. Let's say you're doing an LLM compute. All the optimizations by the compiler cannot be done statically. There are scenarios where compiler cannot know if I can optimize them or no. Those opportunities are there at the runtime though. So imagine at the runtime, it's possible that some full self-attention calculation itself can be skipped together because you know whatever is the outcome of it, it's not relevant. So if that can be known, there are a whole set of algorithms that are coming up as an optimization, and they give orders of benefit in overall throughput that can be achieved by skipping those things. So what you really need is a dynamic runtime controls capability, one, and a good hooks and the smart hooks in the hardware, which will allow it to go by on that one. The third thing is the programming model. Programming model is first order about the convenience and adaptability around it. Let me just say, when I say programming model, imagine in the previous diagram that we are showing, what I mean is the lowest level code where the last level of the intermediate representation talks to the hardware boundary, or one level above the kernel codes itself. So what's the kernel language and the constructs that you use is one aspect that decides it. And then it's the machine code that I talked about. Now, this is the fourth key bullet that I'm mentioning. It's not just about you make the hardware software stack. There are one aspect that is there is, so let's say a new algorithm comes by or a new model comes by. Effort and time that it takes to deploy that application, that is a very key business imperative uh, for that hardware stack to be, the the winning design kind of a thing. The industry acceptance and the stack maturity implies that it has less bugs, it is accepted, there are people who are experts at handling it, and so on and so forth. This is one key point that I want to go a little bit deeper. One is, on one hand, you want that the new model or a new algorithm is embraced in sooner, but at the same time, if you'd like that next 3 months down the line, let's say, you should be able to optimize it further by tuning it further. Does the hardware software stack provides a good way and a good means to tune that? It makes it a very, very compelling thing. And just to compare again, if it takes 1,000 people 6 months to optimize it to a certain level, and vis-a-vis if you compare that 10 people in 3 months are able to achieve that much of a tuning, you can right away see who will be the winner hardware software stack in future around that thing. So to close up with the thoughts, the winner will be one with a mature software stack, the developer adoption, and the adaptability to the new models and algorithms. I missed tunability as well. I'll put that as an important thing here. There can be another kind of an winner as well, I think. One who takes the responsibility of owning the full stack solution till the application level for the specific subsegment, thus making a very compelling offering to the industry to be used up and taking responsibility of everything in between into it. Thank you very much.